The other main definition that we get in this topic 2.1, in addition to average rate of change, is this idea of instantaneous rate of change. So instantaneous rate of change if we said that average rate of change occurs over an interval, it's important that we know that instantaneous rate of change occurs at a single point. And that's really how we would define an instant, just a single point in time. And so that's kind of how you can keep in mind. So if you see anything ever asking for instantaneous rate of change, understand that that's happening at a point. And we can call it A, like we called the interval A to B earlier. Now then, the instantaneous rate of change we said that average rate of change is the slope of the secant line between 2 points. The instantaneous rate of change is going to have the slope of the tangent line to a function at a given point. And we'll get more into this idea of what a tangent line is and how we find it. But it'll be very important that when we start talking about it that you connect it back to this idea of instantaneous rate of change. Now, if you recall from our topic 1.1 in this class, we did this using some very tedious tables where we said, okay, let's look at, we were basically taking the average rate of change, but we were making that interval smaller. And the takeaway we said was we wanted to have the smallest delta x that we could. So if I graph this, just to kind of give you an arbitrary view of what we're looking at, if I have some function here, and we'll just let it look like this here, if I wanted to know what the average rate of change of the function was at this value right here, a, well, I can come up here and say, okay, at this point, I'm at f of a. And what we did was we basically took arbitrary changes in x's, and then we just kept making them smaller. Now that this is one of those things where I'm going to try to format this back to the terminology you're going to see in calculus a lot, I'm going to label this distance here between my two values. I'm going to label it as h. And so if I'm moving, and it's basically the same thing as delta x, if I'm moving h away from a, then this right here is going to be a plus h. And so I have a function value at that is going to equal f of a plus h. And so if I can get it on the screen there, you can see that's exactly what I've got. I've got a change in x of h, and then I've got two different function values here. And so what we can do is we can express instantaneous rate of change as f of a plus h minus f of a over a plus h minus a. And that's what you were doing back in topic 1. You were just taking some sort of value h and adding it to the distance, and we kept making it smaller and smaller and smaller. So in topic 1.1, we used smaller and smaller values for h to approximate instantaneous rate of change. And in fact, if you look right here in my denominator, I've got a plus h minus a. I can actually simplify this down to say f of a plus h minus f of a all over h. And that makes sense because h was my change in x value. And so in order to make this work, we kept making h smaller and smaller and smaller. Well, now that we have a foundation of limits, we can actually use limits, allow us to move away from those tedious tables where we were estimating at the end of the day. Limits are going to allow us to evaluate that expression, this expression right here, we're going to be able to evaluate it as h approaches 0. And if you think about limits, it's not going to be very hard to look at this expression and evaluate it as h approaches 0. And we'll build that in the next video.